evaluation of forecasters using bets, and this was done in collaboration with advisors of Mark, Jonathan, Alex, Ole, and Howard. Okay, so please, thank you very much.
Thank you very much. Good morning, everyone. So I'm László, as many of you know, László Mikolás, and today I will be talking to you about quantifying ignorance and trying to evaluate forecasters by using bets. And today's work is mainly inspired by what the ergodicity economics team does at LML and by what Harry Crane does as well. And I think the best way to motivate today's presentation is with the following quote of one of Harry Crane's papers, which says the following. So, if you wouldn't knowingly invest in a hedge fund whose manager is compensated the same for generating big returns as for going insolvent, then why would you trust claims made by scientists who have little or nothing to lose when their assumptions are wrong, analyses are flawed, or findings are false? And actually, this quote has a lot of, it's a very current, it reflects a very current matter of events, which has actually come to be known as the replication crisis. So recently, many studies have shown that a lot of papers that are published, a lot of results are actually false or incorrect. So for example, in 2015, researchers conducted tried to replicate 100 papers in experimental psychology, and they ended up finding that only 64% of these papers actually replicated. And also in 2016, Nature conducted a poll among 1,500 scientists, and the results they got was that according to 70% of these scientists, they had failed to reproduce at least one other scientist experiment. And a possible reason for these things to happen is that there is quite a big asymmetry in the payoffs that a scientist faces when he publishes. Right? So if he publishes and he's lucky and his discovery hits the mainstream of science, then that's a huge payoff. He becomes famous or even rich. But compared to this, he faces a quite reduced downside for publishing incorrect results. And in the current system, there are actually little or no incentives to actually check that other people's work is right. There are no real incentives to replicate the paper, so even a lot of mistakes might go unchecked. So to try to solve this problem, Harry Crane proposes the following principle, which is called the fundamental principle of probability, which states the following. So if you assign a probability to an outcome happening, then you must be willing to accept a bet offered on the other side that this outcome won't happen at the correct implied odds. So what does this statement mean? I think the best way to illustrate this is with an example. So let's say that my claim is that interest rates will rise, and I state that I claim that the probability of this event is 90%. Then the odds implied by the claim, which are also called the odds against the claim in gambling parlance, are given by this ratio P claim over 1 minus P claim, which in this case is equal to 0.9 over 1 minus 0.9, or equal to 9. And many times we call, for example, in this case, the odds to be 9 to 1. And how do odds work, actually? So if we are offered a bet with these odds, what happens is the following. Let's say that someone bets $1 on A not happening at these odds, 9 to 1. Then what? And he actually wins. Then he will get, if he bets $1, he will get his $1 multiplied by the odds. So he will get $9 at the end. Now note a couple of important properties of odds. First of all, they are increasing in the probability that you claim. So the higher the claim that an event will happen, then the higher are the odds that are implied for the event not happening. This P claim is also called the implied probability by the odds. So if I'm offered odds, I can sort of reconstruct the implied probabilities, the so-called implied probabilities given by the odds. And in this case, if this claim probability matches what I truly believe the probability of the event to be, and I offer you odds given by that probability, then I'm offering you a fair bet. So what the fundamental principle of probability says is that if I make a claim like this with this probability, then I should be willing to offer you the fair odds on a bet against me so that the event won't happen. But the question is, would a scientist really be willing to offer fair odds on a bet against his forecast? And the way to, for example, assess this and to connect with, for example, Ole's example and in Ole's talk, let's say that we have now a sequence of bets where with probability 0.9, the forecaster wins, let's say 5%. So he faces people that bet against him for a fraction of his wealth up to 5%. So if he wins, he takes the money of the bettors. He doesn't have to pay out anything. And with probability 1 minus p, so if the event that he's forecasting, in this case interest rates will rise, doesn't happen, he will lose if he offers the fair bet, the 5% of his wealth that he's risking times in this case, the fair implied odds, which will render a 45% loss of his wealth. Now, how does one go about this to evaluate whether this would be a favorable or unfavorable bet for a forecaster to take? Well, there is a very well-known paradigm, which is the one given by the expected value or the expectation value paradigm. And there's one, which is the time average perspective, which is the most sensible one. But what does the expected value perspective state? Well, what it states is, okay, to figure out if this bet is actually a favorable bet, what you should do is imagine that there are many copies of yourself that live over many parallel universes and go on and bet and do this sequence of betting. And what you should do is average out how the outcomes of the bet come out in these multiple realizations of yourself. So to illustrate this, let's say I think I make 10 realizations of this betting behavior, and what you can see on the right-hand side is the average at each point in time of the evolution of whatever I'm betting on, let it be reputation points or wealth. So we see that still here, I'm not really sure on how these multiple copies of myself would do along time and around all these universes. So let's increase the number of universes I'm checking. So let's do now 100 realizations. We see that now the line is quite flat, and we should also note that it's quite at the initial wealth I have. So seemingly there are no changes to my wealth. And finally, to get an even better picture, what happens if I do 10,000 realizations? Okay, there we go. Now we see that the line is almost completely flat, so we have removed almost all the randomness out of this. And according to this perspective, the expectation value perspective, what it says is that on average, if I could experience all these 10,000 parallel universes of this betting, then on average my wealth wouldn't change, really. The growth rate of my wealth would be 0, so I should be willing to offer you fair odds on a bet against me. But the problem is that no one really experiences these 10,000 realizations of himself. You only experience one, so the right question to answer and the right question to make and which the time average perspective tries to answer is what happens to you, one realization of yourself, which you actually experience over a long period of time. And that's illustrated here. So for example, here we have one realization of this betting for 100 days. On the y-axis we have our wealth or reputation points. We see that for 100 days we don't have a really clear picture of what happens to our wealth. It's still too noisy. What happens in 1 year? Still too noisy. Now what happens in the really long run, in 100 years? So this is what would happen with our wealth over time if we carried on offering fair odds on bets against us. So, and this is something that we would actually experience, and the slope of this line is what we call the time average growth rate, right? So at what rate would your wealth grow if you would offer this bet over a very, very long period of time? So if we compare both, we would see that under this dynamic, no forecaster would be actually willing to offer you a fair bet against his forecast. So we came up with a bit of a different framework to try to capture the essence of this fundamental principle of probability. And for that, we built a model which, again, so capturing this essence of the fundamental principle of probability, has as its objective to make the consistent production of unreliable science an unsustainable strategy for a scientific career. This is also a quote from one of Harry Crane's papers. So for this we built a simple model, okay, which has the following three ingredients. First we have reality, nature, and in reality or nature there is some, let's say, a scientific claim which could be interest rates will rise, and this claim has some true frequency which we call P true. So with P true this claim actually replicates, and with 1 minus P true this scientific claim, or for example interest rates will rise, doesn't replicate. So this is the first ingredient of our model. Then we have a scientist who makes an estimate of what this P true is, so what the true frequency of the claim he's trying to make is. And we assume that the form of that estimation is the true frequency plus some possible systematic bias that he might have. And what he also does is he offers odds to bet against his forecast with an implied probability given by P claim, which might differ from what he estimates. Okay, and then the final ingredient of our model are a population of n possible replicators that can take the scientist on his bet. And the replicators also have some estimate of what this P true or the true frequency of the event is, and that we can illustrate how we model this with the following figure. So the replicators we assume them to be in a neighborhood of, in this case, with 2 eta of the true frequency of the event and evenly spaced. So for example, here we see that the true frequency of the event is 0.6, and we have the estimates of the in this case 11 potential replicators to be between 0.6 minus eta, which in this case is 0.2, so 0.4. So the replicator which has the lowest estimate of the true frequency of the event is positioned at 0.4. And then the replicator that has the highest estimate of the frequency of the event is positioned at 0.8. And we see that they are evenly spaced on this neighborhood of P true. And when would a replicator actually engage in betting against the scientist? Well, the condition that they have to meet is that their estimate is smaller than the claimed probability by the scientist. And why is this condition the relevant condition? Well, because if you recall that the odds offered against an event happening are increasing in the implied probability, then what this means is that for the replicator, what he considers to be fair odds or a fair payoff if the event doesn't happen is smaller than what he's actually being offered by the forecaster or by the scientist. So to him, this is a good deal, a favorable bet. And what we can see here is that, let's say that the claimed probability by the scientist is at 0.5, then the replicators that satisfy this condition are these three, which are positioned below, which have an estimate that is below P claim, so in the interval 0.4 to 0.5. Now to this we add a couple of extra assumptions. So we assume that in each round, the forecaster does make an estimate of P true, and he will offer some odds to bet against him that imply a probability P claim. We also assume that the forecaster knows the width of the region in which the potential replicators are positioned. We assume that this is the behavior, as I mentioned before, of how the replicators decide to take him on his bet or not. And we call M the number of replicators that actually take him on a bet. We assume that when a replicator bets, he risks 1 unit of whatever wealth we consider him to have. And then what we can say is that the payoffs of the forecaster are given by the following. So if the forecaster loses, which means that the event, in this case, happens, he will pay out M, so the number of people that bet against him, a unit amount, times the odds that he offered. And if he wins, he simply keeps the unit amounts that were bet against him. This betting behavior we could call it additive. We call it additive dynamics because the forecaster can win or lose a fixed amount of reputation points at each round of betting. So he either wins M reputation points or M dollars, or he loses M times the odds reputation points. So these are units and are fixed. Now, the important question we have to ask ourselves is, how should the forecaster choose this claim of his in order to maximize his time average growth rate of reputation points or wealth over time? And let's see if, in this case, what we get in comparison to what the fair odds would imply. So for that, we made the following plots. Right, so what you can see in the figure above is the function, is the time average growth rate of the forecaster as a function of his claimed probability. And in the plot below, what you can see is how many replicators start betting against him as a function as well of the claimed probability. And we can notice that there is a quite sort of characteristic shape to how this time average growth rate function looks like, and we can see that this is flat around 0. So there's 0 growth rate for a whole range of claimed probabilities, which actually, as we can notice, correspond to 0 betters. So what this region of 0 growth and 0 better means is that the forecaster is offering odds that are too unfavorable for any bettor to take him on his bet. Then what we see is a region where actually betting starts to kick in. So there are some replicators that start to consider this a favorable bet and then start betting, and we can see that then the number of bettors start increasing. And this has a maximum, and it has a concave shape because there is a trade-off that the forecaster actually faces. So on one hand, he has to offer a higher claim probability, because if it's too low, we see that there wouldn't be any replicators or potential replicators taking him on his bet. On the other hand, if he offers too high claim probability, which would mean that he's offering too favorable odds, so in the region where a lot of people start betting, well, he gets exploited, right? So when he loses big time, so it starts becoming unfavorable for him. And somewhere there is an optimum, which we can calculate. There is a formula for this. So now we can turn to analyze what happens to this time average growth rate function as we modify some of the parameters. So what we see is this is the base scenario, and we have that the true frequency of the event is 0.6. This forecaster is now unbiased, and the width of the interval in which the replicators lie is 1/4, and there are 500,000 replicators. Okay, and one thing to notice is look that the optimal probability to claim for the scientist in order to maximize his time average growth rate is lower, it's around 0.5, than the true frequency of the event, which is 0.6. So this is something important to notice. Now what we will analyze first is what happens if we increase the population. So what happens if now we double the population and we have 1 million potential gamblers? We see that the optimum, the place of optimality doesn't change, but now the peak of this function is bigger. So if he chooses the optimal claimed probability, then he will make more money because there are more people, there's a bigger pool of money from which he can collect. Next, we assess what happens if we shrink the length of the interval in which the replicators lie. So we shrink now eta to 1/10. So we can see two things. First, the peak of this function has become lower. And secondly, the range of possible claim probabilities for which this function is positive has also reduced. But finally, and most importantly, the question that we want to answer is what happens if this forecaster is biased, right? So up to now, there hasn't been any bias, so beta has been 0. Now what we will do is increase this beta parameter, and this is what happens. So the dashed orange figure is the imagined time average growth rate as a function of the claimed probabilities given by a scientist that for some reason is biased and misestimated the true frequency of the event. And what we see, and the most important thing about this figure, is that what he will truly experience is given by the solid blue line. That's the time average growth rate that he will experience. So if he optimizes, as in this case, the orange one, which it's what he believes is true, then, well, he will get a first, in this case, an almost 0 growth rate. But as the bias increases, he would actually experience even a negative growth rate. So this is a very important feature of this model, and with this, I turn on to the conclusions. So we built a model to investigate how this fundamental principle of probability would affect claims made by scientists. We found that the scientists maximize their time average growth rate by making claims that are actually more conservative than what they truly believe, which is something that this principle of probability was seeking. We are seeking that we don't over-report results, right? We want to keep those in check. We found that, that scientists that are biased might experience a negative growth rate of their wealth or reputation points over time if they optimize in that way. And also, something that's interesting about the fundamental principle of probability is that it does generate a mechanism by which, scientists are penalized by over-reporting their results, but also it incentivizes other researchers to try to replicate each other's work. And with that, thank you very much. And I'm open for questions.
Thank you very much. It was a very excellent talk. We have time, 5 minutes for questions.
Yeah, Mansour.
Mansour?
I guess I'm kind of thinking out loud, but what I'd like to see is, well, firstly, thank you for the nice presentation.
Oh, thank you very much.
To get some real data, last few days, US interest rates have been in the news all the time, right? And it's the biggest amount of data you can get. You know, Eurodollar futures tell you about probabilities for the last 20, 30 years. Have you looked at, and also you can tell people make claims about it because everyone today said interest rates are going up. Have you looked at that as a test of your assumptions or your model?
Well, not yet. We haven't done any empirical work yet, but this is for me one of the best databases that you can access. So yeah, definitely that's a great idea and a way forward in this project.
More questions?
Yes.
So if I understood correctly, the scientist needs to know the width of the distribution of the other guys.
In this very simplified setup, yes.
Could you do anything if he doesn't? If he tries to infer that?
Well, this is the natural next step, which would be to introduce some uncertainty of what he believes how the people are spaced along this true.
I guess the biases in how we perceive the people as well as how we perceive our end results.
Sure, and also we could introduce some uncertainty as to not only this bias, but some uncertainty as to how he estimates. So these are both things that we will eventually look into, definitely. Yeah.
The question, I mean, in this context, the replicator bet against you. If he has a probability, if he thinks the true probability is lower than the one between one.
Exactly.
Okay. Maybe, I don't know if it's true because I don't know anything about betting. Maybe more next to reality that they bet only if they think that the event is more likely not to happen. Well,
actually, that is the thing. So, if their estimated probability of the event is lower than yours, then that means that your estimate of the probability not happening is lower than what I think, and so that means that you are wrong to me. So this is that
you're discoverable anyway.
Exactly.
If I think in my own mind what I would do, if someone says that I thought something happened with 90%, and I think it happens with 80%,
yes,
I would bet, and I wouldn't bet anyway, because anyway I think that in 80 out of 20 cases I would lose.
Okay, well,
to me, but I would lose anyway in 80 out of 100 cases.
Okay, well then that's, I mean, I think that's a critique on on the assumption of how they make. Yeah, I mean the thing is that this condition is not some ad hoc thing, but it comes out of seeing when these replicators have a positive time average growth rate. So the conditions that condition comes out of that calculation. So yeah, definitely. But we could, of course, be more sophisticated in the modeling of that behavior. Yeah.
More questions? No. So thank you very much.
Thank you very much.